Hatsios, the pilot, Captain flying the Boeing 777-300 ARX in tonight's flight, the Boeing 777-300 AR airplane airliner. In tonight's flight from Zurich International Airport, we're going to be overflying Zurich, Switzerland, and Germany, and then coming back to Switzerland and Zurich International Airport, runway 14 for landing. So now I'm in the cockpit of the Boeing 777-300 ERX airplane of the PMDG simulations and the Microsoft Flight Simulator X. I'm in the cockpit for the pre-takeoff preparation. So I'm gonna show you the instruments of the aircraft, like the displays, the autopilot flight director system. So we have the flight controls, the thrust levers, and the overhead panel. In the overhead panel, we have the electrical, the hydraulics, the flight control computers, the air data inertial reference unit, the fuel system, the auto start with the electronic engine control computer that controls the FADEX, the full authority digital electronic control computers for the engine. And also we have the wing and engine guides, and we have the cabin pressurization and the outflow valves from the engines and the APU with the compressed air. So you can see the cockpit. We also have the flight control system that includes the yoke of the Boeing 777. As you can see, the yoke is this control column and control wheel that pieces up the elevator up and down in the horizontal stabilizer tail of the aircraft. Also the rudder pedals, the flaps and the slots. You can see I can extend the slots like that. You will see the wings extend. So you can see the flight control surfaces. So we have a lot of instruments, like the displays, the primary flight display that displays the airspeed selected from the autopilot and flight directors system. That is selected for the auto throttle, and also we have the barometric altitude above the sea level, and the altitude selected from the autopilot and the flight director system. The airspeed selected and the altitude selected are for the flight guidance of the aircraft, as well as the heading select and the ILS localizer crossbars in the primary flight display. So we have a lot of information and data. We also have the magnetic and true heading. We have the magnetic north pole and the true north pole, and we have the magnetic variation depending on where we are in the Earth. We have a difference between the magnetic north pole and the true north pole track. So this also affects the inertial navigation of the aircraft using the ADIRU, the air data inertial reference unit in the overhead panel, and also our GPS positioning and inertial positioning when we start the aircraft. So I told you we have the airspeed selected. The airspeed is displayed using the pitot dynamic cubes sensors. In the overhead panel we have the ADIRU, the air data inertial reference unit. The barometric altitude above the sea level is displayed using the pitot static sensor cube. Also in the ADIRU, the attitude display of the aircraft with the crossbars, the flight director crossbars and the autopilot crossbars, and the pitch ladder in degrees and the bang angle in degrees, and also the radio altitude. All this stuff is included in the ADIRU, the data inertial reference unit, as well as the angle of attack of the aircraft and the magnetic compass. So we have the magnetic and true north pole difference, magnetic variation calculations, and the radio altitude above the ground level displays a beam that reflects the ground level below the aircraft. So we also have the flight mode annunciator with the auto throttle and the autopilot commands and mode. so we can engage the vertical and lateral navigation modes from the autopilot panel and display them in the primary flight display for guidance. So you can see here we have the primary flight display with all this information. You can see the airspeed selected from the autopilot and flight director system, the ground speed, the crossbars from the flight director or the autopilot with the flight guidance of the aircraft, the radio altitude, the Lszh localizer for an Lszh localizer landing. So you can see these limits here represent the takeoff speed limits. So we have the heading from the magnetic compass, also the barometric altitude above the sea level, and the barometric pressure. We have the heading select from the autopilot flight director system. We have the altitude select from the autopilot flight director system. We also have a table that represents the rate of climb and descent of the aircraft. That is very important also. Over here we have the rate of climb and descent of the aircraft in tens or hundreds or thousands of feet. Over here on the right, just besides the barometric altitude. So you can see the modes, the flight mode annunciator with the auto throttle and the autopilot modes. We have the navigation display here. So besides the primary flight display, we have the navigation display that displays the airports, the waypoints, the navigation aids like the ABS and the voice stations. And we have the inertial position with the GPS position, and also we have the weather and terrain radar with the reflections of the terrain right now. That displayed with green, yellow, and red the terrain level around us. We have green below, we have yellow about the same altitude as the aircraft, and red above the aircraft altitude. So you can see also the terrain level displayed in thousands of feet. We have the flight plan. We create the runways we use for takeoff and landing, magnetic and true heading, the airspeed, the wind, and also the next waypoint which follows. So we use the flight management computer to create a flight plan, a flight path, vertical and horizontal for the aircraft to follow. I'm going to show you later also that. So this is displayed in the navigation display. So these two displays are the most important for the aircraft navigation because of data, and also in respect of the altitude, horizontal situation indicator, and the altitude of the aircraft. So also the display of the engines, very important. The engines information. So we have the upper and the lower ACAS that display permanent engine information. I'm going to show you in a while. So we have the FIS display also here, the electronic flight instrument system display, the standby instruments display, the autopilot and flight director panel, FDS. I'm going to show you the autopilot and flight director system panel. We have the autopilot engage and disengage, the speed guidance with the speed select node, the airspeed select node, and also the airspeed select modes for the auto throttle, the auto thrust system. So we have the climb continuous, the auto throttle hold, and the flight level change. We have the autopilot engage and disengage, the auto throttle arm left and right, arm and disarm switch, and also we have the heading select node, and also the bank limit select node, and the heading hold switch. We have the vertical rate of climb and descent of the aircraft in tens or hundreds or thousands of feet, and also the flight path angle the aircraft can follow, and also we use a slider for this, and also we have the vertical rate of climb and descent or the flight path angle hold switch. We also have the altitude select node and the altitude hold switch. We have also the VO localizer for the Lszh localizer landing to select the frequency from the selected runway from the flight management computer that we input. I'm gonna show you later. So we can navigate the aircraft from takeoff to cruise down to approach and landing to the selected airport. And also using the ILS localizer for alignment with the runway and the vertical glide slope that we follow the line. So we have also the approach mode for an auto-land approach if we wish to do something like that, and the flight director and on and off. So you can see we have the primary flight display with the flight mode, the annunciator, the airspeed, the altitude above the sea level, above the ground level, this to select, the altitude to select, the ground speed, the heading, uh, the terrain data. Here is the navigation display. You can see the terrain level with green, with red, yellow we have with blue the sea, and also the airports right now displayed. So you can see here we have the Switzerland, here is France, to the northwest. The center is the Switzerland where we are located, and you can see the aircraft symbol, this triangle here. So we also have the heading right now of the aircraft, and we have with red is 6,100 feet the terrain level, with yellow is the intermediate, and 0 feet is with green. So you can see Germany is in this side, in the north and northeast. So here is the autopilot panel I'm telling you. So you can see here we have the auto throttle, left and right, engage and disengage switches, the flight director on and off. We have the airspeed select here. We can select a different airspeed. This is depressible, so we can change select or deselect the mode. This also, the heading is selectable. We can change the heading to a different heading, like the runway heading. We can select a bank angle limit here. You can see. Also, this switch over here is depressible. To select an item, we can press the flight level change here. So here we have display the flight level change, speed and the heading select with airspeed 212 knots, and the altitude select at 10,000 feet. I will select a higher altitude. We can select thousands of hundreds like that, and also hundreds, and select the hold. This will cancel this. We can select the heading and the altitude hold. So we have this for takeoff right now in the primary flight display. These two modes. So you can see how the autopilot is arranged in this display. So you can select the vertical rate of climb and descent here, but apparently you can see the down and the up. So you can select down this way. You can select a descent like minus 4,800 feet, or you can select a climb. So you will see this displayed over here, the VS mode. This is the vertical navigation, this is horizontal, this is the auto throttle mode. So we can select the vertical speed of flight past angle like that, the handling track like that. These small switches here indicate the airspeed or map if we are in a higher altitude. So we can select a descent, minus 2 degrees is trigonometric degrees angles for climb or descent. So you will see the flight path angle here displayed in the vertical navigation. I hope you like the views inside the cockpit of the Boeing 777, as I do. Let's have another view outside. So we have about about an hour left for this flight. So I'm gonna show you as many systems as I can. So I told you we also have the engines. So we have the thrust levers. Uh, we can we can modify the thrust produced by the engines by moving the thrust levers forward or back to the idle position, or forward to the takeoff position, for instance, or the cruise level position. So we select different levels of thrust, like 60, 70, 80% of thrust, depending on what we do, climb or cruise. We need like 75% for cruising with this aircraft. With this fuel level, right now we have 30% fuel, or 46,000 kilograms on board, and plus I think we have like 20,000 kilograms of passengers and cargo. So we have 235,000 kilograms total weight, and depending on the center of gravity position, that balances the aircraft in flight. So we use the horizontal stabilizer trim position, pitch up and pitch down uh, permanently. So we have the auto trim system for that, because this is fly by wire aircraft, and you can use the auto trim to position the horizontal stabilizer trim that balances the aircraft position using the center of gravity. I will show you in a while. So we have the thrust levers. You can see them here. Uh, you can see I can move them forward. The speed brake retracts for takeoff. So you can see we have these displays, the upper ACAS and the lower ACAS that displays engine data. So the permanent engine data displayed are mainly in the upper ACAS engine indication and fuel alert system. Uh, all these data are being monitored and displayed, and also are limited by the FADEX and controlled by the FADEX. The FADEX are the full authority digital electronic control computers, one installed per engine, dual channel, uh, controls all the engine's functions like the fuel flow per engine per hour, the oil temperature, the oil quantity, the vibration of the engine. Also the engine limits, like the N1, which is the low speed, low pressure compressor stage of the turbofan turbojet engine, because this aircraft has two engines for redundancy, one installed per wing, left wing and right wing. So we also have symmetric thrust. We don't want asymmetric thrust between the left and the right wing. So the N1 is the low pressure, low speed compressor stage of the engine. Usually the front fan stage. We have the exhaust gas temperature per engine. We have the direct pressure of the outflow valves from the 5th and the 9th stage of the engine. This is used for the cabin pressurization, for an engine RDI for hydraulic fluid pressurization, and for other systems like the air conditioning and ventilation. And we have the N2, which is the high speed, high pressure compressor stage of the turbojet engine. That is usually the high pressure compressor of the turbine. So this includes many stages with many blades, like usually 5 to 9 stages of blades, like low pressure, 4 stages front fan, and then 9 stages of high pressure compressors and turbines, and the exhaust of the turbofan engine. So this is usually a turbine with a high ratio, uh, bypass ratio is arranged. So it also has a gearbox with the FADEX, the full authority digital electronic control computers that control the engine, using the flight control, the autothrottle system with the flight director and the autopilot, and also the autothrottle with the thrust lever position. and the autopilot commands and the flight management computer input. So it has a lot of stuff in it, a lot of controllers. You can see the electronic engine control computers here with the auto start for the engines, the fuel system here. We have also the fuel system, the pressurized air, how flow from the engines is for the hydraulics here, pressurization. So we have some hydraulic pressurization from the engines, also valves. So it has also engine starters, it has electromagnetic alternators. The engines also produce the electrical current of the aircraft, alternate current 120 volts to 100 volts maximum. So I'll talk to you about that later. I'll show you the thrust levers first and the N1 position. So by moving the thrust levers forward, you can see the N1 here increases, the lowest below pressure compressor stage of the engine, the exhaust gas temperature, the flaps position, the landing gear, the duct pressure, the cambing altitude, the total fuel. This is the upper ACAS. So the lower ACAS also has some messages with yellow and red. The lower ACAS, the N2 high speed high pressure compressor stage of the engine, the fuel flow per engine per hour, the oil pressure, oil temperature, oil quantity, and the vibration of the N2. So you can see we have here, this is controlled mainly by this, the flight director and the auto throttle system for automatic thrust arrangement. So if you want manual thrust, you disengage the auto throttle using these switches over here on this side of the controllers of the thrust levers. So we have the takeoff go on switch, we have the thrust reverse. You can move this up, and we have the thrust reverse slowing down the aircraft from the ground after landing. You can see the thrust reverse being employed here. So you can see here we have the thrust reverse in the outside view. So we disengage the thrust reverse, open it up again. This reverses the flow of the turbofan engines. You can see the exhaust of the turbine with the hot gas, expanding hot gases, and this is how we disarm it. So we have like less than 1 hour. We have like 40 minutes for this flight. So we also have the flight controls here, control column. So we fly the aircraft mainly by moving the thrust levers forward to advance the fuel flow into the engine. This makes the engine spinners faster and faster, intaking more air faster and compressing more air. That creates more high pressure inside the turbine, the high pressure stage. So it burns the fuel and expands the gases which are exhausted from the back side of the engine. So we have the front fan of the engine and the back the exhaust of the engine, and this creates a movement of the aircraft. It creates kinetic energy to the aircraft by converting the fuel energy to kinetic energy. The kinetic energy is 1 second the mass of the aircraft times the velocity to the power of 2. You remember the Newton's physics, and use Newton's physics, some aerodynamics, some aircraft engineering, space engineering, and mathematics. We're gonna talk about this principle. So it creates a motion of the aircraft and kinetic energy into the aircraft by means of action and reaction. If you remember the first, second, and third laws, the Newton's physics. We have the action and reaction by moving the aircraft forward using the expansion of the accelerated gases from the turbine, the left and right engine, turbofan engine. So which makes the aircraft just moving forward, not moving upwards into the sky. It can only accelerate forward with the engine. So you use all the thrust levers to accelerate the aircraft, the engine. So you need to pitch up the elevator. After you acquire some kinetic energy and motion by the thrust of the engine, the thrust overcomes the drag friction from the air as the aircraft moves forward. So the thrust always is equal to the drag using some aerospace engineering. So we talk about the forces, the main forces of flying an airplane, an airliner, a jet airplane airline. So you can see here we have the forward wings of the aircraft, the forward wings of the aircraft, the big wings. You can see the left and right create stability, and also when the aircraft moves forward by the engine propulsion, the aircraft needs, depending on its weight and its configuration, this airplane with this fuel and weight right now, 250,000 kilograms, needs about 154 knots or 270 kilometers an hour in the runway for takeoff to have an effective lift from the forward wing. The lift is the force needed from the Newton's physics to make the aircraft flyable, because it sucks the aircraft up into the air. It creates a vacuum above the wing. So you can see the forward wings. This is what creates the lift for the aircraft to fly. You can see the ailerons and spoilers we use for controlling, for directional control of the aircraft. Also the elevator and the vertical stabilizer. So we have quite a lot of flight controls. So the forward wings, about 35% of the mean aerodynamic force of the wings position creates the maximum aerodynamic lift pressure. It's the center of pressure. It's also the position where the center of gravity is positioned usually at this position, forward or up. So it makes the aircraft balance around this point. So the lower surface of the wing, the bottom of the forward wing is flat. Its surface is flat, so the air travels slower below the wing, and the surface of the wing is curved. It has a curvature above the wing, the top of the wing. So between the bottom of the wing and the top of the wing, there is a difference of pressure as the aircraft accelerates 270 kilometers an hour in the runway. And this creates differential pressure. We have higher pressure below the wing and lower pressure because the air travels faster above the wing, or an air suction, so above the wing. So the air pushes the airflow of the aircraft below the wings and has it has less pressure above the wing. This creates the lift force. The lift force must be equal to the weight of the aircraft times the gravity acceleration, the mg component, using the Newton's physics. So you can see that also here, the wings and the components I'm talking to you about. So this is about 35% of the mean aerodynamic forward position where the maximum lift component is created. It's also the position used for calculating the stall speed of the aircraft and other factors, other components. As I told you, the airspeed of the aircraft must be 154 knots for this weight or higher to overcome the weight of the aircraft using the lift from the wings, and also to overcome the stall speed. The stall speed is an airspeed below which the aircraft cannot create enough lift to fly, so it starts falling down into the ground. So you also have to use flap position and stabilizer, horizontal stabilizer trim. So we use flaps like 15 degrees for this flight or higher, and also we use the horizontal stabilizer elevator surface to pitch off the aircraft. It picks up the horizontal elevator, the horizontal stabilizer here. This creates a moment force. So the horizontal stabilizer and the vertical stabilizer are positioned with angles transversing this axis here, and also the position of the center of gravity and the mean aerodynamic accord of the aircraft. It's about 85% of this position. So the center of gravity should be here, where the mean aerodynamic accord is 35%. It should be forward or aft this position, a little bit, not too much. It will make the aircraft lose its stability inside, or being over more difficult to control. So you can use the vertical stabilizer to turn around the center of gravity, the elevator to turn around the center of gravity, pitch up and pitch down, and also the irons and the spoilers in the left and right wing to bound roll. So the elevator, the horizontal stabilizer and elevator create a moment arm force that is equal to the airflow of the air, to the mass of the airflow times the distance from the center of gravity of the aircraft all the way back to the horizontal tail of the aircraft, or the vertical tail of the aircraft. The same is applied for the ailerons and the spoilers. So you use a moment arm, the moment arm using the Newton's physics or the aerodynamics and aerospace engineering is the force from the center of gravity of the aircraft all the way to the ailerons, the distance. So you have to use the airflow mass per second. So it's a differential. It's you also have to use timing per second to calculate these forces. And sometimes you have to use the components of the aircraft, like the mass of the aircraft times the gravity. Other things like the engine all have its own weight. So it's a lot of calculations. So you can pitch up, you can bank roll, and also I will show you right now. So for doing all these things, I'm using this side stick in here. You can see the Lszh Extreme 3D, so I can pitch up, pitch down the aircraft around its center of gravity on bank roll, left and right around its center of gravity, and use the rudder pedals also to steer. And also for nose wheel steering, and we also can balance the stabilizer trim position and thrust levers position, advance forward and backwards. So you can see pitch up, pitch down, bank roll, left and right. You can see the controls I input here on the screen. I can control the elevator here, and the rudder pedals, and the ailerons and the spoiler. So this creates differential loads between the wings of the airplane as we fly. So we have directional control of the aircraft in flight. I hope you like this, the side stick. You can see the position of the side stick is proportional to the angle of the side stick as I move my hands. So you can also control the stabilizer, the horizontal tail of the aircraft position, to pitch up the elevator or pitch down of the horizontal tail of the aircraft, the ailerons and the spoilers in its left and right wing, and the rudder pedals, and also the thrust. From the thrust levers we need to calculate thrust. So I will turn now inside and make the engine start demonstration after that. So this is for the outside view of the aircraft and the flight control. We have a little bit more. So you can see also you can see the control column and control wheel, the elevator pitch up and pitch down, the ailerons and spoilers, the stabilizer trims here and here, the horizontal tail of the aircraft. You can see the position in degrees, 4 degrees up, and we have the normal and the alternate pitch trim. You can use either this or leave it to the auto. So you can see I'm also using this control column. So every time I move my hands like that, so there is a proportional movement between the side stick and the control yoke of the Boeing airplane. So this is how we control the aircraft in flight. Also the flight controls the thrust levers here. So this is so much for the flight controls lesson. Hope you like it. Pitch up, pitch down the elevator, and bang roll left and right the ailerons and the spoilers and the rudder pedals here in the front of the aircraft panel. So we also use this for the nose wheel steering the ground. We have the flaps also, which are secondary flight controls, which increase the lift of the airplane. So I'm gonna show you a couple more things and do the engine start demonstration very fast. Not much time tonight. So we have like 38 minutes left. So I will say a little bit more of this cockpit view. One more time, you can see this beautiful cockpit view. You can see the autopilot panel here. We can select the values we need for flying the aircraft. Also the autopilot engage and disengage switches. The control switch here is the fuel flow into the engines, left and right engine. The stabilizer trim of the tail for the electric trim from the autopilot and the auto thrust. Cut out switches, leave them in the normal and alternate trim. The speed brake here. Also the flaps position. If we advance the thrust levers, the speed brake retracts automatically, as you can see. You can see the thrust levers position here. We have these warnings here. I'll move back it. Expand it again. I move the flaps up to the takeoff position. Like 15 degrees. We have the alternate flaps. We have the flight management computer. You can see the landing gear here. Alternate gear we can use in case the normal gear is not working. You can see the down and up position, the extend, retract, the auto brake here. Some other I will tell you in another slide about the system. So I will come over here. We can start the APU now, I believe. I'll show you later about that. Not losing time. We have the flight control computers, primary flight control computers, the air data analysis, I told you. That displays the GPS. We have the gyroscopic acceleration and deceleration of the aircraft, the laser gyroscopes, the barometric and the radio altitude, barometric pressure, other data like the airspeed of the aircraft and the altitude, and all this displayed here and here, and also fed to the engine. So we have also here the fire extinguishers, the radio communication panel of the aircraft. So we have the left and the right engine, electrical alternators from the left and the right engine, the hydraulic pumps, the fuel system, the fuel tanks, left and right wing fuel tanks and the center tanks, the exit pumps here for the fuel. You can see the fuel systems here. You can see the left and the right engine feed. We have the fuel jets and we can dump fuel in flight like this. We have the hydraulic left and right engine, the backup hydraulic, some other systems like window sheet. This is circuit breakers. Some other systems here. So you can see the auto start engine, electronic engine control computers, auto start normal. You can start the engines like that. You need to turn this on. Back to the normal, the passenger oxygen with the heat, hydraulic pumps I told you, and this is the cabin pressurization forward and up, outflow valves. We use the automatic or manual using the outflow valves position for pressurizing the cabin when climbing at the pressurized when you descend. This pressurization system here. So we open and close the outflow valves pressurizing the pressurized aircraft. We'll leave it to the automatic right now. Let's see the auto. So here is the left and the right engine bleed air. This is the pressurized air from the engines. The engines also produce electrical current, hydraulic pressure, and pressurized air. Also the APU, the auxiliary power unit, we have it right now. Create some pressurized air from the left and the right engine for starting the engine in the ground. Also, bleeder closed. Also in the auto. And this is used for cabin pressurization, for wind and engine at the ice, for hydraulic fluid tank pressurization, for starting the engines using the APU line only, and also for the air conditioning here of the aircraft. As I told you, and the pressurization of the cabin as we climb, and the pressurization as we descend. We also have wing and engine at the ice here. The navigation lights, lighting system, and the windshield wipers. So we have the electrical here. I will talk to you the flight control computer, process symmetry. So we have the left and right engine produce also alternate current. So we have about 13 plus 18. We have less minutes now. So the left and the right engine also produce alternate current. We have electromagnetic alternators in the gearbox. We have the FADEX and full auto digital electronic control computers in the engines, left and right engine installed. We have our system. So the left and the right engine produce alternate current, 120 volts, 200 volts, 400 Hz frequency, constant alternate current, using each engine bipolar north and south pole, electromagnetic alternator with electromagnetic induction, alternate current. So we can convert this 120,000 kilovolts or 120,000 watts from each left and right engine, or from the APU another 120,000 kilovolts, 400 Hz frequency, again 120 volts to 200 volts. Alternate current, we can convert it, we can use transformer rectifiers to convert into direct current. We have also the batteries that produce another 28 volts but constant current, direct current, no alternate. We can convert also this into alternate current using other static inverters. So we have the APU also for starting the engines in the ground. This switch that produce electric current, alternate, and also pressurized air for the engine starter when it's pressurized air. So you can see the hydraulics here. I will show you one last component. We have this here, so you can see the display. We have the engines right now, the status. You can see the APU is on, so we can start the engine. We have the checklist here, the normal menu. So we have before start what we need to do. This is the items we need to do before starting the engine. So the checklist is complete. We have also other non-normal menu. We have what to do in case we have an engine, an APU failure. So I will show you later. Maybe we have some time. We have the communication, navigation, synoptics. We have the doors of the airplane here of the Boeing 767. You can see where the position I am right now. I have this nice view here. So we have like 10 minutes for starting the engine and for flying the aircraft. We have the doors closed, the cabin can be pressurized, the gear, the tires of the aircraft, the nose wheel, and the temperature of the brakes, the electrical left and right engine, alternators, 103,000 volts, alternate current and direct current from the batteries, also alternate current from the APU. The hydraulic pressurization from the hydraulic pumps, left and engine driven. So if I come here in the overhead panel, you can see if I turn off the switches, we will lose the hydraulic from left and right engine. So you will see here the faults coming down into the upper ACAS if I turn them off. So we have the hydraulic pressure. We lose all the hydraulics right now, the horizontal stabilizer, the tail, all the flight controls. We have alternate flight controls here. So if I come in this view, you can see we have no hydraulic pressure. We also have no flight controls. They're crossed. It's not good. So we can see hydraulic left, right, and center. So we lost these flight controls. No good. Also the rudder pedals. So we'll come here again and restart the hydraulic pumps. I will come over here and restart the hydraulic engine driving and electric driving. So this will cancel the warnings and set the demand to the auto. So you can see the fuel flow here with the Jetson here. This is the left and right engine, left and right wing pump, and also tank and the secondary tank. I will show you later the fuel system, the air system. I'll tell you left and right engine, compressor, and the APU. We have the auto start here, the cargo fire system here. So we'll come again. We have to start the engines now. A couple more. The fuel system, you can see the left and right engine. I'll show you the forward and the aft pumps. Also the quantity of the fuel in thousands of pounds, 46,800 kilograms. The left and the right engine, the fuel valves, low and the high pressure, and the line, the APU also, the direct current, the DC, and the center pump. The crossfeed is on. So the hydraulics is working now, 3000 psi left and right engine. All the flight controls are working. The air system also here. You can see the flight controls now work. It's fully movable. We can fly the aircraft. The air system, left and right engine. We can use the APU pressurized air to start to supply the engine starter. So if I advance the thrust levers here, you will see the pressurized air, the duct pressure increase. So you can see the symbol of the engine and the bleed outflow valve. So this is for cabin pressurization, hydraulic fluid pressurization, wind and engine at the ice, and the air conditioning of the aircraft. So I come here. So we turn off the left and the right engine. So come here, turn off the fuel flow to the engine, left and right engine. So we're gonna make an auto start for the engine. So this is where we are right now. We have a few more minutes to make the engine start very fast. We fly the aircraft also very fast. So you can see the engine start spinning right now. You can see the aircraft, the forward, the right wing, the left wing right now over here. So we'll go back here. You will see the ACAS, the message that the engines are off. The engines are off. So we can see the N2 is going down, the fuel flow is 0. So we start in the overhead panel, the left engine started. You can see the reconfiguration in the overhead panel, some yellow switches. So when we do that, the APU starts admitting compressed air into the engine, the left engine first. You can see also the N2 increases above 20%. So the left engine starts having spinning here. You can see the spin of the engine increases rapidly. You can see the wing here. So we go inside and we start the fuel flow into the left engine. So you can see the N2 increases, the fuel flow increases, and we have the spin of the engine, the left wing engine. So we can start now the other side engine, just to make the aircraft flyable. The other side engine, you can see, is off. So coming in the overhead panel again, starts the right wing engine. You can see the right wing, the N1 increases the pressurization in the exhaust gas temperature. When we have it above the N2 above 30%, we can start the fuel flow above 25% better. The fuel flow is 0 now. We have the engine spinning from the pressurized air. This is the APU pressurized air into the right engine. So we have enough pressurization to ignite the fuel. So fuel flow goes in. So you can see now the engine spinning, the right wing engine. So here we have it, the left and the right wing engine. We have almost everything start. We need only to set up the flight management computer set up. So we have 25 a few more minutes. So we go here in the menu, the FMC, you can see the model, inertial positioning. We need to position an aircraft the reference airport, initial reference, the zero fuel weight and the gross weight and the fuel. You can see performance initialization, the departure and arrival, the route of the aircraft, the departure arrival airport, departure runway. So we copy paste this, runway 14, departure, this runway, Lszh departure, transit, Zoo to Alpha, and the arrival again, ILS 14, next page, next one Alpha, transomically. So we can activate and execute the flight plan line. You only need the reserve fuel 5%, the cruising altitude 35,300. Click over here, you can select, and the course index 100. We also need a couple more, the takeoff reference, 15 degrees flaps with center of gravity. It's automatically calculated 4 degrees up from the computer using the fuel and the weight of the aircraft. This is the takeoff speed, 154 knots. So we are ready for taxiing into the runway, and we have like 4 or 5 minutes and plus 18. So this is the autopilot set, this is the display set. We have some more modes. Use the lights here. So advance the thrust levers a little bit, and disarm the parking brake and go. Use this steerer to steer the aircraft on the ground, so the nose will steer, also the rudder pedal. So the runway is open to us right now. There's no traffic. So parking brakes one more time. You can see the Boeing 777 position here in this runway. That's for takeoff. So you can see the autopilot is set correctly. We use less range here, so you can see the flight plan. It's this line, this purple line. You can see the terrain scan with the yellow and red. The waypoints we have to follow, the flight director, the Lszh. So we advance the thrust levers forward, about takeoff go around position to stabilize the engines. We have the flaps set at 15 degrees. You can see the on1 increases. We have the stabilizer. So we disarm the parking brakes and go. We have like 19 more minutes for this flight. Advance them forward into the takeoff go around position. So we have 18 minutes left. We have the V1, we rotate and go. You can see. Be careful not to strike the tail of the aircraft as we pitch up. You can see we have a positive rate of climb here. We are 600 feet above the ground level. We track the landing gear here and follow the flight plan. You can see we are 1,800 feet above the ground level, 212 knots, 3,000 feet above the sea level. So there is a difference, 2,500 to 4,000 feet. The rate of flight is 70,000 feet. You can see the flight mode annunciator on the mode. So we turn into this line for flying the aircraft. We also have the stall speed. You can see this yellow and red line. It will make the aircraft lose its flying ability and fall into the ground. It will go down to the red limit. So we have to make some stall avoidance. You can see we climb it. Keep climbing. Correct with the flight controls. We're flying. You can see the runway in this side, the airport. We're flying with about 400 kilometers an hour right now, the airspeed. So maybe some outside views here. Hope you like the Boeing 777. We have some outside view. You can see the Zurich here, the Switzerland. We have about 18 minutes left. Some nice night sky view here. The galaxy. You can see we climb out from the airport here. You can see the airport with the runways on this side blinking. Just after takeoff. Hope you like the night view, the night sky, and the view of the Boeing 777 airplane. We fly with about 500 kilometers an hour right now, speed. So this magnificent view The Boeing 777-300 RX. As we keep climbing, we have like 15 minutes left for this flight, maybe a little bit more. Maybe a little bit less. You can see I'm stabilizing using the pitch frame, also the control columns here. It's the waypoints, you can see the climb bar. So we fly with this airspeed Mach 0.4, about 500 kilometers an hour. Climb with 7,000 feet. So I need to reduce the rate of climb right now. You can see the airspeed is decreasing, is going down to the stall speed margin. So we have the stall protection system. It's gonna level off the aircraft for a while until we gain some airspeed. We need to level off for a couple of minutes just to regain some airspeed. You can see the flap limit here. You can see the modes, the speed, the LNAV, the flight path angle. So we need a couple more minutes to climb. We fly with 600 kilometers an hour now, Mach 0.44. Maybe use higher airspeed margins here. So we need to retract the flaps a little bit. Just to have more airspeed automatically. We have like 11 minutes left for this flight. So this is our spacecraft for tonight. The Boeing 777-300 RX. Hope you enjoyed this magnificent view with the galaxies here. This night view, 600 kilometers an hour, about 33,480 right now. 33,500. No, 36,000. So here we have the handrails now and the contrail. This beautiful view, this magnificent display with the frozen vapors. Flying with 600 kilometers an hour or 200 meters per second. So this is our spacecraft for tonight, the Boeing 777-300 RX, overflying Switzerland, the St. Gallen Lake here. And we have the Germany on this side. We are very close to the German borderline. We have no time to overflight Bayern Munich and Bavaria on this side. You can see how beautiful the Germany and the Switzerland are, the Bavarian Alps. So we go back to the cockpit now and coming back for landing now. So here we level off at this altitude and turn back to the airport. So we have like 9 more minutes left for this flight. So we're gonna use maximum thrust as we turn here over flying Germany and Switzerland. 35,000 feet with about 600-700 kilometers an hour, 250 meters a second. I'm gonna fly faster after that. So these are spacecraft for tonight. The Boeing 777-300 ERX. So we arm the autopilot. I go the autopilot. Arrange this next flying direct to. So we're flying direct into this waypoint. I will have the autopilot on. And also the approach landing limits here, the approach reference. So now flying with autopilot on. Have like 7 minutes left for this flight. So I need to make a huge shortcut now for 7 minutes. Completely marginal this flight. So this is our spacecraft for tonight with this beautiful galactic view here. I hope you like the galaxy view. Hope you like the Swiss Alps, the Germany, beautiful view, Switzerland, the lake over here. Flying with 900 kilometers an hour or 300 meters per second right now. This is our spacecraft for tonight. The Boeing 777-300 ERX, so going back. Doesn't need to descend now, very fast. Select a lower altitude here. So we'll descend manually. Extend the speed brakes. We have like 4 minutes left for this flight. So here we are as we're going down to the runway on the airport. Crossing the clouds here. So we have an Lszh localizer here engaged. Lszh localizer landing. You can see the horizontal and the vertical guidance of the airplane. So we have maybe 1 more minute for this video to end. You can see the Lszh localizer here, all the modes of the Lszh localizer. We are aligned a little bit to the runway and the glide slope. We need to descend a little bit faster. I will talk to you in another flight. Not many minutes for this flight right now. So we're going down into the runway for landing. It's about 360 kilometers an hour. Here we are. 10. Here we go. And we are touching down. Parking brakes and reverse thrust, full reverse. Engage the full reverse thrust. So you can see we just landed in runway 14, the Boeing 777-300 ERX airplane. Thank you for watching me. It was a magnificent flight. So you can see we have the landing gear here. The nose wheel completely safe, no damage from the landing. So that was Thomas, that is the pilot captain behind the Boeing 777-300 ERX. Thank you very much for watching us. See you next time. Bye bye.